Module 3, Lecture A, Lists and Tuples. By the end of this lecture, you will be able to describe how Python lists are implemented and how that affects operation complexity. Analyze the time complexity of common list operations such as append, insert, and slice, and differentiate between lists and tuples in terms of mutability, usage patterns, and performance. Python list internals. Dynamic array basics. A Python list is a dynamic array managed by the interpreter that stores references to objects in a contiguous block of memory. You can imagine it as a row of numbered boxes, where each box holds a pointer to an object. Because the elements are stored together in memory, the interpreter can quickly calculate the position of any item and access it directly by its index. This contiguous layout is what makes indexing operations on Python lists very fast and efficient, regardless of the list's size. In Python, lists are implemented as dynamic arrays, which means they can grow and shrink while the program is running. Memory is reserved in fixed-size chunks that usually hold more elements than the list currently uses, so new items can be added quickly to the next free slot. This design makes lists feel flexible and almost limitless while still benefiting from the speed of contiguous memory. When all reserved slots are filled, Python resizes the underlying array to create more space. A Python list automatically resizes when it runs out of space by allocating a larger block of memory, copying the existing elements into it, and releasing the old block. This occasional resize step is more expensive than a normal insertion, but it does not happen every time you add an item. Because of this dynamic resizing strategy, accessing elements by their index remains consistently fast, while some insertions may occasionally take longer when a resize is triggered. Amortized list appends. Appending items to a Python list may look like it always takes the same time, but the underlying behavior is more complex. Lists are backed by dynamic arrays that reserve extra space, so most appends are fast because they simply place a new element in the next free slot. When that extra space is used up, Python must allocate a larger block of memory and copy all existing elements, which is slower. The idea of amortized appends explains that these occasional expensive operations are spread out over many cheap ones, so the average cost per append stays low. Understanding this helps you better predict performance when building large lists. Python makes list appends efficient by over-allocating space when it resizes the list. Instead of adding just one new slot each time, it grows the underlying array by a larger factor. This means most append operations are very fast, and only occasionally does Python need to allocate new memory and copy elements. By spreading the cost of these expensive steps over many quick appends, the average time to append an item stays low. When we talk about amortized behavior for list appends, we mean that even though a single append may occasionally trigger an expensive resize, the average cost per append is still constant. As a result, building large lists, such as sequences of sensor readings or user inputs, remains efficient overall. The total time to perform many appends grows roughly in proportion to the number of appends, even if individual operations sometimes take longer. Understanding this lets you confidently use lists for growing sequences while still being aware that resizing can matter in performance-critical situations like real-time loops. Python code, amortized list appends. We want to demonstrate amortized list appends by running a simple timing experiment. The goal is to show that even though some individual appends may be slow, many appends in a row stay fast on average. To do this, we compare the total time it takes to build lists of different sizes using repeated appends. By examining how the total time grows with list size, we can see that the average cost per append remains low overall. This line is a comment that recommends installing several common Python libraries used for data analysis, machine learning, and scientific computing. The current script does not actually use these libraries, but the comment reminds the user to prepare a more complete Python environment. This setup can support more advanced or complex tasks in future projects. In short, it is about ensuring the user has a robust set of tools ready, even if they are not needed in this specific script. We begin by importing the time module so we can measure how long operations take to run. This module offers precise timing tools that let us track the duration of specific parts of our code. In this script, we use it to record how long it takes to append items to lists. By doing this, we can better understand the performance of these list appending operations. We define a helper function that measures how long it takes to append many items to a list. At the start, it records the current time as the beginning of the timing. It then creates an empty list and runs a loop from 0 up to the given count. During each loop iteration, it appends the current integer to the list, gradually building up the dataset. The loop ends once all integers up to the specified count have been added. After all the append operations are complete, we stop the timer using a high-precision performance counter to record the end time. We then subtract the recorded start time from this end time to find how long the appends took. The result is the total elapsed time in seconds for the entire append process, which we return as the final measurement. We define a list of target sizes for our experiment using 1,000, 10,000, 100,000, and 1 million elements. These values let us study how the total time for appending items changes as the list becomes larger. By testing across this range, from relatively small to very large lists, we can observe how list append performance scales with size. The code first prints a header message to the console to tell the user what the upcoming output represents. It explains that the program is about to show how long it takes to build lists by repeatedly appending elements. This message provides context so the user understands that the numbers that follow are timing results. In short, it prepares the user to interpret the performance data that will be displayed next. We test list append performance by trying several different list sizes and timing how long it takes to build each list by adding elements one at a time. For every size, we record the total time spent appending. We then find the average time per append by dividing this total time by the number of elements and converting the result to microseconds. This lets us see how the efficiency of appending changes as the list grows larger. This code prints a neatly formatted summary of a list building operation, showing the list size, the total time to build it, and the average time per append. It uses formatted string literals to align the size within a fixed width field so the output stays consistent even for large numbers. The total time is displayed in seconds with 4 decimal places, and the average append time is converted to microseconds, also with 4 decimal places. Together, these values give a clear, precise view of how efficient the append operations are. This script illustrates amortized time complexity by timing how long it takes to build Python lists using repeated append operations. It creates lists ranging from 1,000 to 1,000,000 elements, measures the total time to append simple integers, and then computes the average time per append in microseconds. The results show that even as the list size grows dramatically, the average time for each append stays very small. This demonstrates that Python's dynamic list resizing makes append operations efficient on average, even for large lists. Resizing and memory overhead. When a list resizes, it balances flexibility, performance, and memory use by reserving extra space instead of growing one element at a time. This means it can add new elements quickly without constantly asking the system for more memory. The trade-off is that the list may temporarily use more memory than it strictly needs. Only when the reserved space is filled does the list resize, which requires allocating a larger block of memory and copying the existing elements. But this happens infrequently enough that most append operations remain efficient. When a list runs out of space, it must allocate a larger block of memory and copy all its elements, which is slower than a normal append. To reduce how often this happens, lists usually grow by multiplying their size instead of adding one slot at a time. As a result, most appends are very fast, and only occasional resizes cause a brief slowdown. Overall, appending to a list is generally efficient, but sometimes the list must do extra work to expand its storage. Lists often use more memory than the data strictly requires because they keep extra space available to make appending new items fast. This deliberate overallocation is usually a good trade-off since memory is relatively cheap and the performance benefits are important, especially for continuous data like sensor readings or logs. However, in memory-limited environments or with very large datasets, this overhead can become a problem, and list growth and reuse must be managed more carefully. Understanding this behavior helps you see why it is beneficial in most cases and when you need more precise control over memory use. Python code, resizing and memory overhead. We want to show how a list grows in memory when we keep adding elements to it. As we append items, the underlying storage sometimes needs more space, which triggers occasional expensive resizing operations. This behavior also creates extra unused capacity beyond the elements actually stored. Visualizing this difference between allocated space and real content helps explain both list resizing and its memory overhead. The comment recommends installing the ptuple library, which is useful for checking memory usage. This can help you analyze how much memory a list uses as it grows. Even though the script does not directly call ptuple, the comment points out that you could use it for more detailed memory analysis than what the basic code provides. We begin by importing the system module so we can interact with the Python runtime environment, which is necessary for tasks such as checking how much memory different objects use. We also import the time module, which provides tools for working with time. In this context, we use it to measure how long operations take, allowing us to analyze the performance of list resizing. Together, These modules let us study both memory usage and execution time in our Python program. We define a helper function called measure_appends to time how long it takes to add items to a list. At the start of this function, we record the current time using a high-resolution performance counter so we can accurately measure short durations. We then create an empty list that will store items as we append them one by one. By doing this, we can observe how the list grows and how the time required for each append operation may change as the list becomes larger. The code defines several checkpoints to measure how long it takes to append items to a list at key stages: the beginning, 1/4 of the way, halfway, and at the end. These points are chosen to show how performance changes as the list grows. An empty dictionary is created to store the recorded times at each checkpoint. This timing data is then used to analyze how list resizing affects overall performance. We run a loop from 1 up to the total number of items, and in each step, we add the current index to a list to simulate the list growing one element at a time. As the loop runs, we check whether the current index matches any predefined checkpoints. When it does, we record how much time has passed since the loop began. These recorded times show how long it takes to reach specific list sizes and can reveal delays caused by list resizing operations. This code uses the system module's size function to find out how much memory a list uses measured in bytes. The result tells you the size of the list container itself, not the memory used by the items stored inside it. This distinction helps you understand the overhead of the list structure in memory, separate from the data it holds. The code starts by printing a brief summary of the current operation, using a label to identify it. It then reports how many items are in the list by checking its length and calculates how many bytes the list container uses in memory. This reveals the memory overhead of storing the elements. Finally, it records timing checkpoints during the appending process to show how long different stages take and to highlight any slower operations when the list resizes. The code goes through each checkpoint and its recorded elapsed time in the dictionary, and for each one, it prints how much time has passed since the appending process began. By showing these times, it highlights when list resizing may have occurred. This makes it easier to see how those resizing operations could have slowed down performance and to understand the timing of those slowdowns. We call a function that measures how appending elements to a list affects its resizing behavior and memory usage. We ask it to append 20,000 items, which is large enough to make the changes easy to observe. We also pass a descriptive label, list resizing demonstration, so we can clearly identify the output from this run. This setup lets us see how Python grows a list over time and what memory overhead is involved during the append operations. This script explores how Python lists resize and use memory when many items are appended. As integers are added one by one up to 20,000 elements, it measures the time taken at certain points, revealing that some appends are slower because the list must occasionally resize its underlying storage. It also tracks the list's memory usage, showing that Python allocates extra capacity beyond the current number of items. Overall, the example illustrates typical dynamic array behavior, where occasional costly resizing operations help balance speed and memory efficiency. List operation costs, indexing, and iteration. In Python, indexing is a key concept for working with lists. A list is stored in a continuous block of memory, so the interpreter can jump directly to any element based on its position. This direct access makes reading or updating an element at a known index very fast. Importantly, this access time stays roughly the same whether the list has a few items or millions of items, aside from small, hardware-related differences. When you iterate over a list, you visit each element one after another, so the work grows directly with the number of elements. If you double the length of the list, the time it takes to go through it roughly doubles as well, which is why this is called linear time. Tasks like searching for a value, computing a total, or applying a transformation to every item all scale in this linear way. Understanding this helps you predict how performance will change as your lists get larger and you design algorithms that make repeated passes over them. Understanding the difference between constant time indexing and linear time iteration is key to writing efficient programs with lists. When you frequently need specific positions, such as the latest sensor reading or a computed index, lists work well because accessing an element by position takes constant time. But tasks that scan the whole list, like filtering data or finding a maximum, take time that grows with the list's size. In real applications, such as log processing or video analysis, recognizing when to rely on direct indexing and when to avoid unnecessary full traversals helps you maintain good performance as your data grows. Python code, indexing, and iteration. We want to show how list operations differ in how their running time grows. First, we time list indexing to demonstrate that accessing an element by its position takes about the same time no matter how large the list is, which is constant time. Next, we time iterating through all elements of a list to show that the time increases in direct proportion to the list size, which is linear time. Finally, we compare how the total work changes as we repeatedly double the list size, highlighting that constant time work stays flat, while linear time work roughly doubles with each increase in size. The comment about installing NumPy, Matplotlib, and Seaborn explains that these libraries are not required for this script. It indicates that the script is intentionally simple and self-contained, meant to demonstrate concepts without extra visualization or numerical tools. This keeps the code straightforward and easy to use. The comment also serves as a reminder that such libraries are helpful for more advanced work, but are unnecessary in this basic example. We begin by importing the time module, which provides tools for working with time in a program. In this context, it is used to measure how long certain operations take to run. By timing tasks like indexing and iteration, we can accurately track their duration. This helps us understand and compare their performance. We begin by creating a large base list with 1 million elements, generated using a range of numbers starting at 0 and going up to, but not including, 1 million. This list acts as the common starting point for our timing experiments. By using such a large and consistent list, we can more accurately measure and compare how different operations perform as the size of the data grows. The code sets up a list of integers that represent different list sizes used for testing. These sizes allow the program to measure how long indexing and iteration take for small versus large lists. By comparing the timing results across these sizes, we can see how performance changes as the list grows. The code prints a header line that labels the columns of a timing results table. It shows the size of the list being tested, the time for indexing operations measured in microseconds, and the time for iteration operations measured in milliseconds. This header makes it clear how to interpret the performance data that follows. The code runs a loop over a list of different sizes, and for each size it measures how long certain tasks take. This setup is used to compare the performance of indexing and iterating over lists as their length changes. By systematically testing each size and recording the timing results, the code shows how the performance of these operations scales with increasing list size. We create a new list called current by taking only the first n elements from the base list. This slicing step ensures that, for each test, we work with a list of a specific size. By repeating the tests with increasing values of n, we can observe how performance changes as the list grows larger. This method keeps each test consistent and makes it easier to compare results across different list sizes. To ensure fairness when measuring how long it takes to access a list element, the code always selects the element in the middle of the current list slice. It does this by dividing the list size by 2 and using that position as the index. Choosing the midpoint avoids bias that could occur if the element were always taken from the beginning, the end, or a random position. This consistent choice makes timing results more reliable and comparable. To measure how long multiple index operations take, we first record the current time using a high-precision performance counter from the time module. This gives us an accurate starting point for the timing. After the indexing operations finish, we can compare the new time to this starting value to calculate the total duration of the process. In this part of the code, we repeatedly access elements in a list to measure how long indexing operations take. A loop runs 100,000 times, and in each iteration it reads the element at the middle position of the current list slice. By performing this middle index access many times, we ensure the total runtime is long enough to analyze and compare indexing performance. To measure how long the indexing operations take, the code records the start time using a high-precision performance counter from the time module. After the indexing finishes, it records the current time again and subtracts the start time to get the duration in seconds. It then multiplies this duration by 1 million to convert it to microseconds, giving a more precise measurement of the indexing time. We begin by recording the current time using a high-precision performance counter from the time module. This timestamp marks the start of a full pass over the current portion of the list. After the loop finishes, we compare the new time to this starting value to find how long the iteration took. This approach lets us measure the efficiency of iterating through the list. We begin by setting a running total to 0, which will store the sum of the list elements. Then we loop through each item in the current portion of the list and add its value to this total. By visiting every element and including its value, the process ensures that the final total represents the sum of the entire list slice. To measure how long an iteration takes, you first record the current time using a high-precision performance counter. After the iteration finishes, you record the time again and subtract the starting time from this value. The result is the elapsed time in seconds. You then multiply this value by 1,000 to convert it to milliseconds, which is a more convenient unit for timing how long the iteration over the list took. The program reports the size of the list being tested, then shows how long indexing takes in microseconds and how long iteration takes in milliseconds. This output demonstrates how the time for these operations increases as the list grows larger. The times are rounded to 1 decimal place for indexing and 3 decimal places for iteration to make the performance differences easy to see. This script tests how list indexing and iteration scale in Python by working with slices of a large list of 1 million elements. For each slice size, it repeatedly accesses the middle element many times to measure indexing speed, and separately iterates through the entire slice while summing its elements to ensure every item is visited. The timing results show that indexing takes roughly the same amount of time, regardless of list size, while iteration time increases in direct proportion to the number of elements. Overall, the experiment confirms that list indexing is constant time, whereas iterating over a list grows linearly with its length. Mid-list updates. Updating the middle of a list means inserting or deleting elements somewhere other than the end, while keeping everything in order. This is like adding a seat in the middle of a theater row, where everyone has to shift over. In a list, that shifting corresponds to moving elements in memory. As the list grows, more elements must be moved. So these middle insertions and deletions become increasingly costly, not because each move is slow, but because there are more and more of them. When you insert a new priority customer near the front of a long-ordered list, every customer from that point onward has to shift 1 position to the right, and removing someone from the middle forces everything after them to shift left. With a small list, this is fast, but with millions of entries, it can require moving nearly 1 million elements. This makes updates in the middle of large lists expensive because the time they take grows in direct proportion to how many elements must be shifted. In contrast, simply reading or overwriting an existing element does not require shifting others and is therefore much cheaper. When programs frequently insert or remove items near the beginning or middle of a list, performance can slow down because many elements must be shifted each time. In contrast, adding or removing items at the end of a list is usually much faster since it avoids this shifting work. Recognizing this difference helps you spot performance bottlenecks and decide whether to change how you access data or to use a different data structure that handles frequent mid-list updates more efficiently. Python code. Mid-list updates. Demonstrate how the time cost of inserting and deleting items in the middle of a list changes as the list grows. Clearly compare the time needed to insert at the front of a list with the time needed to append at the end. Show how these operation times increase with larger list sizes, so learners can see how performance scales. This line recommends installing optional packages such as NumPy, Matplotlib, and Seaborn, which are useful for numerical work, plotting, and data visualization. If you want to expand the script for graphical analysis or more advanced data handling. These tools can enhance what you do with the data, but they are not necessary for the script's main purpose. The current script only needs the standard library to measure the time performance of list operations. This script starts by importing Python's time module, which provides functions for working with time. Here, it is used to measure how long certain operations take to run. In particular, the code times how long it takes to insert or append elements to a list. By recording these durations, the script can show the performance impact of different list operations as the list grows in size. We define a timing function to measure how long it takes to insert an element at the front of a list. It takes the list size and the number of repetitions as inputs, then repeatedly creates a list of the given size and records the high-resolution time just before and just after inserting a value at the beginning. Each time, it computes how long that single insertion took and adds this to a running total. After all repetitions, it divides the total time by the number of repeats to get the average duration. This average gives a reliable estimate of the time cost of inserting at the front of a list. This function measures how long it takes to append an element to the end of a list. It repeats the operation many times, so the timing is based on an average rather than a single trial. For each repetition, it creates a list of a given size, records the time just before and just after appending one element, and adds the difference to a running total. At the end, it divides the total time by the number of repetitions to return the average time required for the append operation. The code defines a list of three sizes: 1,000, 10,000, and 100,000 elements. These sizes are used to test how long it takes to update lists of different lengths. By comparing operations like inserting or appending items across these sizes, the code illustrates how the time cost of list updates increases as the list grows larger. The code repeats each timing measurement 20 times to improve accuracy. By running the same operation multiple times, it reduces the impact of random fluctuations in individual measurements. This allows the results to be averaged, giving a more stable and reliable estimate of how long each operation takes. The code prints a header for a table that explains what is being measured. It labels one column for the size of the list, another for the time to insert an element at the front, and another for the time to append an element at the end. This structure makes it easier to compare how the performance of these two operations changes as the list size increases. For each list size, we measure how long it takes on average to insert an element at the front using a timing helper. Then, measure the average time to append an element at the end with a similar helper. After collecting these two timing results for the current size, we output the list size along with the average front insert time and the average append time. The values are printed in a neatly aligned format, so it is easy to compare performance across different list sizes and between inserting at the front and appending at the end. This script compares how long it takes to insert an element at the front of a list versus appending one at the end. It tests lists of different sizes and repeats each operation several times to get an average time. The results show that inserting at the front becomes much slower than appending as the list grows larger. This highlights that inserting at the front is less efficient because all existing elements must be shifted, while appending at the end is much faster. Slice and copy costs. When you slice or copy a list, Python creates a new list that holds references to the original elements. The time it takes depends on how many items are in the slice, because it must allocate space for that many elements and copy each reference. It does not depend on the total size of the original list. So whether you slice 10 items from a list of 1,000,000 or from a list of 20, the main cost comes from copying those 10 elements. Making a full copy of a list means creating a new list of the same size and copying every element reference. So the time it takes grows in direct proportion to the list's length. For small lists, this may not matter, but with large datasets, each copy has to touch every element. If you do this repeatedly, especially inside loops, it can become a serious performance bottleneck. Understanding this helps explain why frequent list copying can slow down large-scale data processing applications. When you slice or copy a list, you create a new list object, which increases memory use in proportion to the number of elements, even though only references are duplicated. This is helpful when you truly need a separate subset of the data, such as focusing on a specific time period in a larger dataset. However, many overlapping slices or copies can cause significant time and space overhead. Whenever possible, consider using indices, iterators, or views over the original list instead of making new lists. By remembering that each slice or copy has a cost based on its length, you can design more efficient code as your data grows. Python code, slice and copy costs. This script measures how long list slicing and copying take using simple timing examples. It demonstrates that the time cost of a slice depends on the length of the slice itself, not on how large the original list is. It also compares the cost of taking a partial slice with the cost of copying an entire list across different list sizes. No extra installation commands are needed because the script relies only on Python's standard library. The script starts by importing the time module so it can measure how long operations take to run. By recording the time at the start and end of a process, it can calculate the total duration. This timing is used for performance testing, specifically to see how long it takes to slice or copy lists. We create a very large list to simulate many temperature readings in Fahrenheit by generating numbers from 1 to 1,000,000 and converting this range into a list. This large list serves as a test case for working with big datasets. It lets us examine how operations such as slicing and copying behave and how efficiently they run when the amount of data is very large. This kind of setup is common in data processing tasks, where performance matters. In this example, we build a smaller list of temperature readings in Fahrenheit using a range of numbers from 0 up to, but not including, 20,000, and then convert that range into a list. This compact list serves as a test case for slicing operations on a list with fewer elements. By working with this smaller list, we can measure and compare how long slicing takes on lists of different sizes. To measure how long a slicing operation takes, we use a helper function that records the time just before and just after the slice is created. It uses a high-resolution performance counter from the time module to capture these two time points. The function then subtracts the start time from the end time and returns this difference. This result tells us the duration of the slicing operation on the list between the given start and end positions. We are measuring how long it takes to slice 10 elements from a large list. To do this, we call a timing helper function that performs the slice and records the elapsed time. We provide the large list along with the start index of 100 and the end index of 110. The function returns the time taken for this slice, and we store that result so we can compare it with other timing measurements later. We are measuring how long it takes to slice a small portion from a list. In this case, we take 10 elements from a larger list, starting at position 100 and ending at position 110. A timing helper function records how long this slicing operation takes, and we store that time in a variable. This experiment helps us understand the cost of slicing a small number of elements, independent of the total size of the list. To measure how long it takes to copy a large list, we use a helper function that times slicing operations. We give it the list as the source and specify that the slice should start at the first element and end at the last, which creates a complete copy. The function returns the elapsed time for this full copy, and we store that time for later comparison with other operations. In this step, we measure how long it takes to copy an entire small list using slicing. A timing helper function is called with the list, starting at index 0 and ending at the list's length, which produces a full copy. The function returns the elapsed time for this slicing operation, and we store that time so we can compare it with other results later. This example measures how long it takes to slice 10 elements from a very large list and then rounds the result to 7 decimal places for clarity. The key idea is that the time needed depends mainly on how many elements are sliced, not on how big the entire list is. In other words, slicing a small portion of a list takes about the same time whether the list is large or small. This example measures how long it takes to slice 10 elements from a small list and then rounds the result to 7 decimal places for clarity. The key idea is that extracting a small slice has roughly the same time cost no matter how large the overall list is. In other words, the time to slice a few elements does not grow significantly with the size of the list. The code measures how long it takes to copy an entire large list by slicing it from start to end. It uses a previously recorded time value for this full copy operation. That time is rounded to 7 decimal places to make the result precise and easy to read. Finally, it prints the rounded time along with a message explaining that copying such a large list is a relatively costly operation. This code measures how long it takes to copy a small list and prints that time. It formats the result to 7 decimal places using a rounding function so the timing is clear and precise. The key idea is that copying a smaller list is faster, showing how list size affects efficiency. This material explains how slicing and copying lists in Python differ in time cost. Using one very large list and one smaller list, it shows that taking a small slice, such as 10 elements, takes about the same time no matter how big the original list is, because the cost depends on the length of the slice itself. In contrast, copying an entire list takes much longer for the large list than for the small one, since the time grows directly with the total list size. The script measures these times with the time module and prints the results to highlight that small slices are efficient, while full list copies become expensive as lists grow larger. Practical tuples, immutable tuple guarantees. Tuples are immutable, which means that after you create one, you cannot change, add, or remove its elements. This immutability keeps the data stable and predictable as it moves through your program. Because a tuple cannot be altered when passed into functions or between components, you can trust that its contents stay the same. For example, using a tuple for geographic coordinates helps prevent accidental changes that could corrupt important data in large systems. Tuples are useful in programming when you want related values to stay fixed once they are set, which supports data integrity and predictable behavior. For example, storing order details like product ID, purchase price, and timestamp in a tuple preserves the original record even if other parts of the system later change prices or preferences. Unlike lists, which can be modified and make it harder to track changes over time, tuples remain constant. This immutability helps reduce bugs from shared mutable data and makes it easier to reason about how a program behaves. Tuples are immutable, meaning they cannot be changed after they are created, which makes them useful for sharing and reusing data across a program. Because they never change, different modules can safely reference the same tuple without worrying that it will be modified. So there is no need for defensive copying. This is helpful for storing stable information such as configuration settings, like screen resolutions or access permissions that many parts of a system rely on. As a result, tuples simplify how developers think about shared data, improve performance by reusing the same structure, and support clarity and correctness in complex software systems. Python code, immutable tuple guarantees. This material explains how tuples in Python are immutable and why that matters. Using simple geographic or ordering examples, you can show that once a tuple is created, its contents cannot be changed, which prevents accidental in-place modifications. In contrast, lists are mutable, so their contents can be altered unexpectedly if the same list is shared across different parts of a program. Because tuples cannot be modified, sharing them between functions or modules avoids these unintended side effects. No extra libraries are needed beyond the Python standard library to demonstrate these behaviors. We represent a geographic coordinate as a tuple that holds 3 pieces of information: the latitude, the longitude, and the location name, such as New York. A tuple is immutable, which means that once we create it, its contents cannot be changed. This immutability helps protect data integrity by ensuring that the stored geographic information stays consistent throughout the program. In this example, we represent a geographic coordinate using a list, which is a mutable data structure. Unlike a tuple, a list can be changed after it is created, The list holds three pieces of information: the latitude, the longitude, and the location name. Here, New York. This approach gives you flexibility to update any of these values later, if needed. We begin by printing the contents of both the tuple and the list to show that they start with the same data, even though they will not behave the same way. The key difference is that a tuple is immutable, so its contents cannot be changed after it is created. In contrast, a list is mutable, which means we can modify its elements. This contrast in mutability sets the stage for understanding how each structure is used differently in a program. We try to change the first element of a tuple that stores a geographic coordinate, but this is not allowed because tuples are immutable. Attempting this modification raises a type error, which means the data structure cannot be altered after it is created. We place the operation inside a try-except block so that when the error occurs, it is caught instead of stopping the program. The except block then prints a message explaining that the modification failed and identifies the error type as type error. This example shows how tuple immutability works and how exceptions can be used to handle invalid operations safely. We change the first element of a Python list to a new value, 41.0000, and the change succeeds because lists are mutable. Mutable means their contents can be altered after the list is created. When we print the list again, the first element is updated, confirming that the list has changed. This behavior contrasts with tuples, which do not allow their elements to be modified once created. An order record can be stored as an immutable tuple containing three parts: a stock keeping unit as a string, a price as a floating point number, and a date and time as a string. Because the tuple is immutable, its contents cannot be changed after creation. This ensures the order data stays stable and consistent whenever it is accessed by different parts of the program. In this example, two different modules access the same order record by assigning the same tuple to two separate variables. One variable represents the view from module A and the other from module B. Because tuples are immutable, neither module can accidentally change the underlying data. This means the order record stays consistent and unchanged, even when it is shared across different parts of the program. Module A prints a view of the order record and shows that it is accessing the same underlying data as the original tuple, confirming that the data stays consistent. Module B then prints its own view and also sees the same stable data. Together, these views demonstrate that using immutable tuples for shared data keeps the information unchanged and prevents accidental modifications in any part of the program. The code prints a message to confirm that both module views of the order record stay the same. This stability comes from storing the order as an immutable tuple. Because tuples cannot be changed after they are created, any shared view of that data will always show the original values. As a result, the program can rely on consistent and unaltered order information across different parts of the system. This material explains the difference between immutable tuples and mutable lists in Python. It shows that both can store the same geographic coordinates, but trying to change the tuple causes an error because tuples cannot be modified after creation, while the list can be updated without problems. The script then uses a tuple to represent an order record that is accessed by two different modules, and because the tuple is immutable, both modules always see the same, unchanging data. This immutability helps maintain consistent shared data and prevents unintended side effects in larger, more complex programs. Tuple dictionary keys. Tuples make good dictionary keys because they are immutable, so their contents do not change and their hash values stay stable for reliable lookups. As long as each item inside the tuple is itself hashable, such as numbers or strings, the tuple can be used as a composite key. This allows you to look up dictionary values based on several pieces of information at once. The immutability of tuples keeps the dictionary's mappings consistent over time, which makes them a dependable choice for keys. Tuples make excellent dictionary keys when you need to model relationships or multi-dimensional data with fast lookup. For example, you can pair a city and a year to access climate data, or combine a user identifier with a date to get that user's activity summary. In scheduling, a tuple containing a room, day, and time slot can uniquely identify a reservation and quickly show whether a room is available. In all these cases, tuple keys act as compact, unchangeable records that capture the necessary fields without requiring more complex data structures. Using tuples as keys in dictionaries encourages a careful data modeling style and brings both performance and correctness benefits. Because tuples are immutable, you must create a new tuple to change any attributes, which helps prevent accidental key changes and dictionary corruption. Their hashing and comparison are efficient, so lookups remain fast even when tuples contain several simple, hashable elements. Overall, lists are better for collections that need to change over time, while tuples are better for fixed, hashable groupings used as identifiers or composite keys in dictionaries. Python code. Tuple dictionary keys. This material focuses on using tuples as dictionary keys in a safe and effective way. It explains that tuples, unlike lists, are suitable as keys because they are immutable, which makes their behavior in dictionaries predictable. It highlights how tuple keys can act as composite keys, such as combining a city and a year to store climate measurements. It also briefly notes that you may need to install any required libraries before working with these examples. We can store climate data in a dictionary by using tuples as keys, where each tuple combines a city and a year. For instance, the pair of Boston and 2020 might map to an average temperature of 55.3 degrees Fahrenheit, while Boston and 2021 maps to 54.8. This structure lets us associate a specific value with each city and year combination. Tuples work well as keys because they are immutable and hashable, which makes dictionary lookups consistent and reliable. In this example, a dictionary uses a tuple containing the city Boston and the year 2020 as a key to look up the average temperature for that place and time. Tuples work well as dictionary keys because they are immutable, meaning they cannot be changed after creation. This immutability makes them reliably hashable, which ensures consistent and efficient access to the stored climate data. This line of code prints the average temperature for Boston in the year 2020, the value was previously looked up in a dictionary using a tuple that combines the city and year. The printed message clearly identifies the city and year, then reports the temperature in degrees Fahrenheit. This provides a simple, easy-to-read result for the user. In this example, we create two variables that each store the same tuple containing the city Denver and the year 2019. In Python, tuples with the same elements in the same order are considered equal. Because tuples are immutable, they are also hashable, so they can be used as keys in a dictionary. This means identical tuples can be used interchangeably to access or update the same dictionary entries, giving consistent behavior. In this example, a dictionary uses a tuple as its key, combining the city Denver and the year 2019. The value stored for this key is 49.1, representing Denver's average temperature in 2019. This shows that tuples, because they are unchangeable and hashable, work well as dictionary keys. Using tuples in this way lets us store and look up data efficiently based on multiple pieces of information grouped together. In this example, we look up the temperature for Denver in 2019 using a dictionary whose key is a tuple containing the city name and the year. Because tuples with the same contents are considered equal and are hashable, we can create a new tuple with the same city and year and still access the same dictionary entry. This shows that tuples work reliably as dictionary keys, consistently retrieving the correct value as long as their contents match. To show that lists cannot be used as dictionary keys, we try to create a dictionary using a list that holds the city Miami and the year 2022 as the key. Because lists are mutable, they are unhashable and therefore invalid as dictionary keys. When Python processes this, it raises a type error, which we catch in an exception handling block. This example highlights that dictionary keys must be immutable types, such as tuples, rather than mutable ones like lists. This code reports an error that happens when you try to use a list as a dictionary key. It identifies the error type as a type error and then retrieves the accompanying error message. The message explains that lists are unhashable, which means they cannot be used as keys in a dictionary. Finally, the code prints both the error type and the message to clearly show the user what went wrong. This code prints all the entries in a dictionary to show how tuple keys can be used to store and access data. It turns the dictionary items into a list so you can easily see every key and value at once. Each key is a tuple that combines elements like city and year to uniquely identify an entry. By displaying these items, the example demonstrates how tuples work well as composite keys in dictionaries for more complex data structures. This script shows how tuples can be used as dictionary keys because they are immutable and hashable. It builds a dictionary where each key is a tuple containing a city and a year, and each value is the average temperature. When the script accesses the data, it demonstrates that two tuples with the same contents are treated as the same key, so they reliably retrieve the same value. It then tries to use a list as a dictionary key, which causes a type error and illustrates that lists are unhashable and cannot be used in this way. Finally, it prints all the dictionary entries to demonstrate the practical use of composite tuple keys. Tuple performance trade-offs. Tuples and lists differ mainly in flexibility versus performance. Tuples are immutable, so their contents cannot be changed, which lets Python store them more efficiently in memory and access them quickly. This makes tuples well suited for fixed data, such as coordinates, that do not need to be updated. When you need to change, add, or remove items frequently, this immutability becomes a limitation, and lists are usually the better choice for dynamic collections. Tuples and lists both provide constant time access by index and take linear time to iterate over, but they differ when you modify them. Lists are efficient for adding or removing elements at the end because they can grow and shrink dynamically. Tuples, on the other hand, must be recreated and copied whenever you change them, which is more expensive. As a result, lists are better for dynamic data that changes often, while tuples are better suited for static data that stays the same. When choosing between tuples and lists in performance-sensitive code, focus on how the data will be used. Tuples work best for fixed, read-heavy data, such as stable records, because their immutability and memory efficiency are beneficial there. Lists are better for dynamic data that changes over time, such as task queues or evolving search results, since they support efficient in-place updates. In short, use tuples for stable data with modest performance gains, and lists for flexible, write-heavy situations where frequent modifications are needed. Python code, tuple performance, trade-offs. This section compares the performance of tuples and lists using simple timing tests. It highlights that repeatedly extending tuples is costly, while appending to lists is much more efficient. By observing these timing differences, you can better decide whether to use a list for data that changes frequently or a tuple for data that stays fixed. The goal is to help you choose the right sequence type for dynamic versus static workloads. The script explains that you do not need to run any pip install commands because it only relies on Python's standard library. This means all required features come from built-in modules, so no extra packages are necessary. As a result, you can run the script without additional setup, which makes it easier to use and more accessible. We use Python's time module to measure how long parts of our code take to run. This module is part of the standard library and provides functions for working with time. By recording the time just before and just after a specific operation, we can calculate its duration. This timing information is important when we want to compare the performance of different data structures, such as lists and tuples. We define a function to measure how long it takes to repeatedly append items to a list. It first records a precise start time using the performance counter from the time module. The function then runs an outer loop a chosen number of times, and in each iteration it creates a new empty list and runs an inner loop that appends a value to this list a set number of times. After all these repetitions are finished, it records the end time with the performance counter again. The function returns the difference between the end and start times, which is the total duration of the list appending process. This function measures how long it takes to repeatedly grow a tuple in an inefficient way. It starts a timer. Then, for a given number of repetitions, it creates an empty tuple and repeatedly extends it by creating a new tuple each time an element is added. Because tuples cannot be modified in place, every extension requires building a brand new tuple, which is slow. After all repetitions are finished, the function records the end time and returns the total time spent on these tuple extensions. We repeat the entire process of building a list or a tuple 50 times to simulate multiple scenarios and get a more reliable measure of performance. For each repetition, we perform 200 operations, meaning we add 200 elements to the list or the tuple. This setup gives us a consistent workload that lets us compare how efficiently lists handle appending elements versus how tuples handle being extended. We start by timing how long it takes to build several growing lists using a helper function that measures the speed of list appends. This function is given the number of repetitions and the number of operations in each repetition, and it returns the total elapsed time. That timing result is stored for later use, so we can compare how efficiently lists perform these operations compared with tuples. We measure how long it takes to repeatedly build larger and larger tuples in an intentionally inefficient way. A timing function is called with the number of repetitions and the number of operations per repetition, and it returns the total time in seconds. This experiment shows the performance cost of using tuples for dynamic workloads. It demonstrates that tuples are less efficient than lists when data needs to grow or change frequently. This code measures how long it takes to append elements to a list, allowing you to compare performance for changing or dynamic workloads. It reports the total time used, rounded to 6 decimal places, so the result is precise and easy to read. By examining this timing information, you can better understand how efficient list operations are, especially when comparing them with other data structures such as tuples. This code measures and prints how long it takes to repeatedly extend tuples, showing that this operation is slower than appending to lists. It also rounds the reported time for tuples to 6 decimal places to make the result easier to read. Overall, the output demonstrates that tuples are inefficient for dynamic data growth compared to lists. This line reports how many times slower tuple growth is compared to list growth in the experiment. It does this by dividing the total time for tuple operations by the total time for list operations. The result is rounded to 2 decimal places so it is easier to read, and the phrase "time slower" is added to clearly state the performance difference. This script measures how long it takes to grow a list compared to a tuple by repeatedly adding elements. Because lists are designed for efficient dynamic resizing, appending new items to a list is very fast. Tuples, however, are immutable, so extending them requires creating a new tuple each time, which is much slower. The results show the total time for each operation and how many times slower tuple growth is than list appending, emphasizing the need to choose data structures based on whether your data will change size frequently or stay mostly fixed. In this lecture, you learned to describe how Python lists are implemented and how that affects operation complexity. Analyze the time complexity of common list operations such as append, insert, and slice. And differentiate between lists and tuples in terms of mutability, usage patterns, and performance. In the next lecture, Lecture B, we will go over dicts and sets. Thank you for your attention. See you all in the next lecture.